Welcome to today's lecture where we are going to continue our discussion regarding flow nets. So to give you a quick overview of what we have been discussing, let's consider that a pipe which is filled with a certain soil. Now the flow nets that we studied last time consist of two basic components, the flow lines and the equipotential lines, where the flow lines represented by green lines and the equipotential lines represented by red lines. We also studied that the space between two flow lines is known as a flow channel or a flow path, whereas the space between two equipotential lines is represented by a potential drop or an equipotential drop. We studied the main characteristics of flow channel, that the amount of water flowing through each flow channel is constant. Means that whatever is the amount of water flowing in flow channel number 1, same will be the amount of water flowing through flow channel number 2 and flow channel number 3. In the same way, the head loss between two equipotential drops is the same. So whatever is the head loss in this space, same will be the head loss in any of the other spaces in this figure. So these are some of the basic concepts that we studied in the last class. Now, the important thing that we have been discussing in many of our previous classes is that in the seepage studies, one of the most important requirements for us is to determine the discharge, to determine the total quantity of flow required, flow of water through the soil. So by using flow nets, how can we determine the total flow of water through the soil? This can be determined by making use of the simple equation written here. Now this equation, which represents the flow of water through each flow channel, so we have 3 flow channels here. If we want to determine the flow of water or the discharge of water through any one of these flow channels, we can make use of this equation, in which what we have to do is we have to make use of the hydraulic conductivity or the permeability of the soil, the head loss across that flow channel, and ND is a parameter which represents the number of potential drops. What do we mean by number of potential drops? As we know that this space is known as a potential drop or an equipotential drop. So for example, in this figure, we can have 1, 2, 3, 4, and so on potential drops here. As you can see that this equation gives us the amount of water flowing through a single flow channel. So if we want to determine the amount of water flowing through all these flow channels, what we can do is we can simply multiply this. We can simply multiply this with the number of flow paths or the number of flow channels, that is NF. So if we multiply our equation with the number of flow paths, we can determine the total flow of water through this stratum. So by making use of this simple equation, we can determine the total discharge of water through the soil. Now, how can we determine this NF? How can we determine this NF? Now, determining NF is very simple in this figure. You can easily tell me that there are 3 flow channels over here, but there can be a little more complicated cases. So let's have a look at slightly more complicated case for the determination of flow channels. For example, let's have a look at this figure. Now, how many flow channels are there? You can see there is flow channel number 1 over here. We can say there is flow channel number 2 over here, and there is a third flow channel which is going here, with this being an impervious layer. Now, as you know that the basic characteristic of flow channels or flow paths is that the amount of water flowing through each flow channel would be the same. But by looking merely at the shape of flow channel number 1 and flow channel number 2, you can say, okay, the same amount of water would be flowing through them because this segment and this segment are of the similar shape, but if you see, this segment is of a very different shape. So do you think that the same amount of water would be flowing through through this segment as was the case for the previous two segments? No, it would not be true. So what we do is, in order to determine the number of flow channels, the basic criteria given here can be adopted. If our flow channel consists of square components, we can use NF equals to 1 for that channel. For example, this channel number 1 consists of almost square components, so we can use NF equals to 1 for this flow channel. Similarly, for flow channel number 2, since it is composed of almost square components, so we can give again associate an NF value of 1 for this flow channel. But looking at this one, the shape is very different. The shape of this one is again very different. So what we have to do is we have to make use of this simple formula which is given here. So NF in this case is simply the ratio between width and length of each flow channel. So for example, what I can say regarding this flow channel is that the length is more than twice the width. So what I can do is I can make use of this simple relationship, and by using this simple relationship, I can determine the NF value. And I can say that the NF value, which equals width over length or length over width for flow channel number 3 would be around equal to 0.38. What do we mean by this 0.38? It means that this width is approximately 0.38 times the length, or this average width, you can say this average width is approximately 38% of the length. So length is more than twice the width. So this is what we mean. And practically speaking, it is not very difficult to determine. From this example, since we are dealing it in an online session, it might look a little complicated, but whenever we draw a flow net, we always draw it on a graph paper or on a scale. So you can see we also have a certain scale given here. So if we have drawn this on a graph paper where we know the proper scale of this thing, so all we have to do is we have to measure this length of this component and this average width of this component and divide them to get this value. So we can do it either with this one or this one. Obviously, we are going to get slightly different answers, but you can get an average value to determine the NF value for this channel. So once you have determined the NF value, you can easily determine the total flow by using this basic equation. So let's solve some numericals and some problems and see how can we determine the different components using these flow nets. So the problem given to us is, it states that there is a sheet pile structure and the flow nets for this sheet pile structure are given. The permeability of the stratum in both directions, in the horizontal and the vertical direction, is given. Now the question part A says that what will be the height of water above the groundwater if the piezometers are installed at point A and point B. So if we install a piezometer at point A and we install a piezometer at point B, what will be the height of water in each of these piezometers? So it means that what we want to know is we want to determine the piezometric head, or we want to determine the head of water at these points. Part number 2 says that we need to determine the total rate of seepage through the permeable layer. So we want to determine the total discharge of water from this upstream side to this downstream side using the flow nets. And lastly, we have to determine the approximate hydraulic gradient at this point C. So obviously, as we have seen that we have only used a simple equation so far, so we are again going to make use of the same equation for solving this. Let's have a look at this numerical in a stepwise manner. Let's see how we can solve this part, part A. And this part A says that we have to determine the height of water above the ground surface in the piezometers at point A and at point B. So what we can do is that we have to first dissect that how many equipotential lines do we have. So if we look, we have one equipotential line going here. We have the second equipotential line here. This is the third equipotential line and the fourth equipotential line. If I ask you what is the head of water at the ground surface here, so you can see that the head of water here is 5.6 meters. So the head of water, it means that if I put a piezometer here, the height of water in that piezometer will be equal to 5.6 meter. So the head of water here is 5.6 meter. Now the water flows from this surface and exits at the downstream end. And once the water exits at the downstream end, the head of water only remains as 2.2 meters. Means that on the upstream end, the head was 5.6 meters, and on the downstream end, it is only 2.2 meters, means that it has lost some energy while moving from the upstream side to the downstream side. If there was no energy loss, the head of water on the downstream end would also have been 5.6 meter. But because of head loss, because of energy loss, the head of water is obviously going to be less here. So if I ask you that what is the total head loss from while the water moved from the upstream end to the downstream end, so it would be very simple for you to determine the total head loss. Total head loss would be equal to this 5.6 minus 2.2, and this way you can easily determine the total head loss to be equal to 3.4 meters. Now, if the total head loss is 3.4 meters as the difference between these two, and you also know another characteristic of equipotential lines, that there is same head loss in each equipotential space. So whatever is the head loss in this first equipotential space, the same would be the head loss in the second equipotential space, third, fourth, and so on. So by using this, we can determine the each equipotential drop by using this simple relationship. So we know that the total head loss is 5.6 minus 2.2 meters, which is this total head loss. And I want to determine the head loss in each equipotential space. So since I have 6 equipotential spaces, for example, this is equipotential space number 1, number 2, number 3, 4, 5, and 6. So because I have 6 equipotential spaces or number of potential drops, so I'll put 6 here. This way I can determine the head loss in each equipotential space. It means when the water was moving from one point over one equipotential drop, it was losing 0.567 meters of head. While moving from it through each equipotential drop, it was losing 0.567 meters of head. So this is the first step. Now, if we have determined this thing, it would be very easy for us to determine that what would be the head at point A and what would be the head at point B. Now, if you want to determine the head at point A, it is very simple that the head at point A would simply be the head at the ground surface, which is 5.6 meters, minus the minus 1 equipotential drop, which is 0.567 meters. So this is how we can easily determine the head loss at point A. In the same way, if we want to determine the head loss at point B, what we can do is the head loss at point B would be the total head at the surface minus head loss at a single equipotential space, which is 0.567 times the number of potential drops, which we would require to reach point B. So we would require 1, 2, 3, 4, and 5 potential drops to reach point B. This is why we put 5 here, and this will be the level of water in the piezometer if we'll install a piezometer over here. So what it means, what these two answers mean for us is that if we install a piezometer at point A, the height of water in the piezometer will be 5.033 meters. Similarly, if we install a piezometer at point B, the height of water in the piezometer B would be 2.765 meters. So this is quite simple how we can determine the total head, how we can determine the piezometer level at each point. Let's look at the second part of the problem. And the second part of the problem says that we determine the rate of seepage through the permeable layer per unit length. Now, in order to determine the rate of seepage or the total flow, we have to make use of this equation. And if you see this hydraulic permeability, the hydraulic conductivity is given to us in the problem statement. This head we have already determined, and D, which is the number of potential drops, we already know, and NF, which is the number of flow paths, we have already determined over here. So by putting all these things in the basic equation, we can determine the discharge. So if you see here, this K, which is the hydraulic conductivity, has been inserted here. Then H, which is the total head loss, which we have determined already from here, which is 5.6 minus 2.2. We have determined here as well. Number of potential drops we have already determined. There are 6 potential drops. And this 2.38 actually represents NF, which is the number of flow paths. So what we mean by this is that this is one flow path, this is flow path number 2, and this third flow path, because this third flow path does not have perfect squares, so its contribution would be around 0.38. So in this way, we can simply add these values up for each flow channel. So one for flow channel number 1, another one for flow channel number 2, and 0.38 for flow channel number 3. So you add these up and you come to 2.38. So this solves the second part of the problem for us. Now let's see how can we determine the average hydraulic gradient at point C. So this is point C. Our objective is to determine the average hydraulic gradient. As you know that the hydraulic gradient has a simple relationship, and this is the head loss over a certain distance. So head loss over a certain distance can again easily be determined by using this equation. And you see, head loss, if we want to determine the average hydraulic gradient over point C, so let's assume that we are determining the head loss over these two equipotential paths. So we know it is 0.567, we have already determined, and this length L we can determine from geometry. As I have already told you that we generally draw these flow nets on a graph paper or on any scaled diagram. So if it is any scale diagram, so we can easily determine this length, which is already given to you in this problem. So simply by inserting the values over here, we can determine the average hydraulic gradient as 0.138. So this solves our problem number 1 for the day. Now, another important aspect that you should be aware of whenever we are talking about seepage studies beneath in the dam structure, so there is one important phenomena that occurs when the water flows beneath the dam body. Now let's assume that this is a concrete dam, and if it is a concrete dam, there is minimal flow of water, or there is no flow of water through the dam body, and all the water is flowing only beneath the dam body. Now when the water flows beneath the dam body, there is a certain characteristic that this flowing water exerts an uplift force on the dam structure. Now, this uplift force, which acts on the dam structure, can actually destabilize the dam structure. If the uplift force becomes so strong, it can lift the whole dam upwards. So, when you are doing some analysis of the dam or designing a dam, you need to calculate what is the magnitude of the uplift force, and you have to design accordingly. Now, by using flow nets, we can determine the uplift force acting on any dam structure. Now, how can we determine this? First, you need to remember that this is the general profile of the uplift pressure. The uplift pressure, which is generally represented by symbol U. So if we want to see that what will be the uplift pressure at point A, so this is going to be approximately the uplift pressure at point A, B, C, D, and E. What I actually want to emphasize here is that if you look closely, that while we are moving from point A, that is from the upstream end towards the downstream end, the uplift pressure keeps on decreasing. It means near the upstream end, there will be high uplift pressure, and away from the downstream end, the pressure is considerably smaller. So this is a general characteristic, because once the water is traveling from the upstream end towards the downstream end, it would have lost some energy. There would be a lot of head loss. So because of the head loss, the uplift pressure would be less at the downstream end compared to close to the upstream end. And again, this uplift pressure can easily be determined by using this relationship, where the uplift pressure equals the head available at this point times the unit weight of water times gravitational acceleration. So by determining all these things, you can easily determine the total uplift pressure. So let's solve one more example, and let's see how to make good use of the knowledge that we have gained so far. So this example shows a dam structure with a lot of piezometers installed at point A, B, C, D, and E. So we have a number of piezometers installed at different locations across this geometry. What we are required to do is we are required to determine the pressure head, which is HP, and the total, which is the piezometric head for each of the points A to point E. And as the second part of the problem, we need to determine the uplift pressure acting at the base of the dam at point C. So these are the two objectives that we need to achieve. So let's see how we can solve part number one, which is how can we determine the pressure head, which is HP, and the piezometric head, which is the total head at point H, at point A first, for example. Let's see how we can determine these things at point A. Now, in order to determine the pressure head at point A, it's quite simple. The pressure head at point A represents the height of water in the piezometer because of the pressure exerted at point A. So because of the pressure which is being exerted at point A, water has risen up to 19 plus 7 meters. So the pressure head at point A would be equal 26 meters. I repeat this thing, that the pressure head at point A would be the height of water in the piezometer because of the pressure which is exerted at point A. So since our total height of water is 19 plus 7 meters, so this would be our pressure head. In order to determine the total head or the piezometric head, so we know by definition of the total head equals the pressure head plus the elevation head. So in this case, in our particular case, there is a slight difference here though. So this pressure head is relatively simple for us, that the pressure head we have already calculated as 26 meters. However, in case of elevation head, Or rather, a more simple way of determining the piezometric head is simply to see that what will be the height of water above the required datum. So in case of dam studies, we generally take the downstream water level as the datum surface. So it is a common practice to take the downstream water level as the datum surface. So in order to determine the total or the piezometric head, all you have to see is that what is the height of water above the datum. So as clear from this figure, the height of water from the datum is 19 meters. So will be our total or the piezometric head. In the same way, if we want to determine the pressure head and the piezometric head at point B, we can follow a similar thing. So the pressure head at point B would simply be the height of water because of the pressure exerted at point B. And this would mean the total height of water from point B to the top of water level. So for this, you have to add these two up and we'll get 34 meters. Whereas when we talk about the total head or the piezometric head, we have to see that what is the height of water above the datum surface, which comes out to be 15 meter. And here is our answer. In the same way, we can determine the pressure head for and the piezometric head at point C, at point D, and at point E. So there is no significant difference. However, you will see that when we talk about point E and we want to determine the piezometric head at point piezometric head or the total head at point E, so the total head at point E would be 0 because the height of water above the datum surface is 0. So the total head or the piezometric head over here would be 0. Now moving to second part of the problem, that how to determine the uplift pressure at point C over here. In order to determine the uplift pressure, we have to make use of the simple equation that we have used earlier. So for in this, the uplift pressure U is equals the head times unit weight of water times the gravitational acceleration, and we can simply insert all the values over here to get our uplift pressure. So replacing all the values here, the pressure head at point C is 20 meters. So 10 and 10, it becomes 20 meter is the pressure head, the unit weight of water, and the gravitational acceleration. By converting the units and coming to a consistent units, we get the answer of the uplift pressure. Means 196.2 kilopascals of uplift pressure would be acting at this point. So that's it regarding today's lecture. Thank you very much.